Hey guys and girls, welcome to my Godot outline tutorial. We're going to be making outlines for pictures in Godot. It's a pretty simple procedure, so if you're looking it up then you probably don't have much experience with visual effects or shaders in general. But that's what we're here to cover. So I'm just going to do a short explanation of how we create these effects before walking through an implementation of code to do them. Yeah, it's important to have some grasp about what you're trying to accomplish with a piece of code, so you can later on, for example, modify it for your own particular needs. Before we do anything else, the 0th step is to actually make sure our image is on all right sides. You see, Godot won't actually render an image outside the bounds of its texture, so try as you might, if your image is too big, you won't actually be able to do any outlining. If you have this problem, just go to your favorite image editor program and just copy it into a bigger file. Big enough at least for the outline that you eventually want to give it. Also make sure that any negative space are transparent pixels. So, now that we have our image, let's just drag it in to the project. Click it. Go to Material under Canvas Item. Click Material and go press New Shader Material. And create a new shader for it. So what is a shader? Basically, the GPU of your computer is the part responsible for displaying all the visual stuff you see on screen. In the context of games, all the code that you write in script and the stuff supporting that, i.e. physics and whatever, are instructions for the CPU. However, a shader script compiles instructions to your GPU to directly tell it what to render. The reason why we use the GPU is because it actually does a lot of calculations in parallel, making it fast, but putting several limitations on it. In Godot, shaders are written in a completely different language. The most immediate thing that we have to do is write shader type, canvas item on top. They tell the GPU we're going to be doing stuff in 2D. Now, let's plan our implementation. We're just going to go through every pixel within the texture. And if it's empty, we look around for the closest non-empty pixel in its vicinity. And if that distance is less than line width, then we change this empty pixel's color to the outline color. So let's actually start implementing it. The first thing we're going to need to type in is declare some variables. So we'll go uniform float line width equals 1.0. So what we've done here is that we declare a variable that we can actually pass into the shader through traditional script or to the editor that we'll use to modify the code. And you can also do that again for to declare what color we want our outline to be. So by default, we'll just make it vec for 001, which corresponds to the RGB value of a solid black line. Okay. It's also going to be really helpful for us to declare a constant variable pi, which is mathematical number pi. You'll see why later on. A couple decimal places should be fine. Okay. So, we want to run a function every pixel, right? And the function that does that in JavaScript is the function that runs every single pixel and can change every single pixel is Fragment. So type in void Fragment. Then we're going to want to declare a float called alpha. So now, of course, and then we're going to want to declare a 2 vector called scale, which returns the returns the size of a pixel in the relation to the UV of the texture. So the UV of something of a texture is basically a number from 0 to 1 for both dimensions. That corresponds to how far along the texture it is. The reason why we do this and not like pixel by pixel is because we might want to scale up the texture, for example. So it makes sense to just use proportion rather than like broad pixel size. Okay. So now we do a for loop to get so we want to. So we're not actually going to be able to look in all infinity directions away from the point that we're searching for. So we're just gonna have to do it for a couple different angles. To do this, you can go for use simple for loop int I equals 0. I is less than a number called angres, which we'll just define as a constant under pi. Const. No, actually, let's use snake case. Let's be a little bit consistent here. I wanted to use snake case only for uniforms because it looks good in the editor, but usually prefer. But now we'll just do it here to be consistent. 16. Say actually, let's make it 8 for now. So I is less than I plus. We'll just say, oops, don't forget to write int. Then we declare the type of variable that it is. So float angle is equal to 2 pi 2.0 times 0.0 is important because it tells the script that it's a float, not an int, which it doesn't like. Times float I divided by angles. I just said about casting. Okay, and then we're going to want to define another variable, direction. No, sorry, not direction. Displacement. Which is simply the unit vector of the direction of angle. Do that here. Cos angle, sine angle. Wow. And don't forget to multiply this first by scale, and then also by line width. Oh. This way the displacement is scale times line width away from. So it's line width pixels away from the pixel that we're scrutinizing, and we multiply by scale to convert into UV. So what we do is we then fetch the color of the pixel we're looking for by fetching the color of the texture that we've loaded up at position UV plus displacement, and texture is how we fetch it. Then we copy its alpha value. We add its alpha value to alpha. So then, now the for loop's done, we type in at the bottom if alpha is greater than 0, and we change the color of this pixel to outline color. Otherwise, we render it. We just the color is the color of the texture at this pixel, which is what usually gets run. Go down here. Wow, it looks like an outline there. That being said, if you zoom in real close, you can see that like some portions here aren't exactly declared as alpha equals 0 because of artifacting from the art program. So it might actually behoove you a little bit to make the threshold slightly above 0.0. So make it like maybe 0.2. Don't make it too high. Okay, you can also increase the. Of course, you can also increase or make it a little bit less blocky. The outline is by increasing the angres 16 or something. Depends how much time you want to waste on your per shader. And also, we can go to the right hand side of the editor and under shader params, and from there, not from script, change the line width value away from its default of 10, say 20, double it, 5. I think actually I like it a little bit better. I can also change the color of the outline. Wow, it's red now. Now it's yellow. That's amazing. So yeah, that's just a simple outline. Pretty straightforward, pretty simple. Okay. Now things can actually get interesting. So, one of my favorite things that animators do is that they redraw the same frame over and over. So even though the character is not moving, it actually looks really energetic. I think it's cute. Whatever. I don't know what it's called, but we're going to try and simulate it using outlines. For each pixel, break the time that the shader's been running into discrete time steps. Get a random value based on that time step and the pixel's position. Use that random value to get the outline width between min width and max width. Look out outline width in every direction. It's pretty much the same thing as the basic outline after that. Okay, here we are back in the editor. To make our changing outline thing, we're just gonna take what we've already made and duplicate our outline material. I call it changing outline material, I guess. Why not? Now we're going to change line width to max line width and min line width, and then we're going to create another function called which is returns a float called get line width. It's going to take into inputs p, a point, and a float s for seed, and then but we'll implement this later. All we're going to do right now is return the linear interpolation of the halfway point, the average of max and min line width. Of course, comma, not semicolon. Excellent. Here, let's do get line width UV and time. Actually, even better, we can create another float called time step, which is just a floor time times the frequency we want our outline to update, which we'll just define as as a uniform up here, and use time step. For style purposes, let's just cut and paste this. Okay, so now we just need to get the random value for get line width. Whoops. We can't just use the UV directly into get line width. We need the raw pixel that we're going to need. So instead, we're going to go scaled UV. We're going to create a variable called scaled UV, which is just the UV divided by the scale, the texture pixel size. Now we're just going to go scaled UV. Yeah. And multiply by the end of the texture pixel size. It's very fun. Okay. Now I have to convert it back into UV form. So now we just need to implement get line width. And to do that we need random values. But how do we get this random distance? Well, we're going to need two things. First is something called a hash function. You see, true randomness is pretty much impossible for computers as far as we're aware for now. So instead we're going to settle for a function that takes a point and a seed value and outputs a seemingly random value in relation to those, between 0 and 1. To accomplish this, we're just going to run the dot product of the inputs through a sine function, and then take the fraction of the result. If the coefficients are big enough, it should look more or less completely random. Next, we're going to need a noise function that smooths out the hash function, so that adjacent positions get similar values. To do this, we need to break the possible positions into grids of size block size, then get the hash values of the 4 corners of that cell that the pixel is in, and linearly interpolate them based on the point's position within the cell. This ensures that adjacent pixels are smooth, but independent from points in other grids, more or less. This technique is actually how we do other seemingly random visual effects, like lightning, or even an image-wide offset. So to break P up into block size, we're going to first declare a uniform called block size, of course. I set its default value to like 20-ish. And we want to divide P by it. Bruh. And for the noise function proper, it's going to take in the pixel value that has been block sized. Yeah, dividing P, by dividing it by block size, you break up every whole value, every sequence of block size into values between 0 and 1. That's why we do division. Okay, first we want to define a vector 2, D, which just holds 0 and 1, and a vector 2 called B for base, which is the floor values of P. And a vector 2 called F, which stores the fractional values of P. So like how far along P is across the cell, across the block, I guess, that you define. Then what we're going to want to do is we're going to want to get the hash value of the top right corner. So sorry, the top left and top right corner. So hash B plus D plus vector 0, 0, which is the same as dxx, or D, the first value of D twice, S, and hash B plus D, or plus 1, 0, which is D xy, and then we're going to linear interpolate the whole thing accordance to how far along P is in the x-axis, f.x, and we're going to want to do the same thing with the bottom left and bottom right corners. So it's y, that's y, so then we're going to interpolate that how far along the y-axis P is. And then we just return the whole thing. Return. Wow. I think good style looks like this, maybe? I'm not sure. I'm trying. Okay, and then get line width instead of returning this just the average of max and min. We're going to want to return mix of we're going to want to define a float L or float W even, which is shorthand for weight of noise P and S. Then we're going to want to interpolate over W, of course. Yep. So it'll be some random. So the width will now be some random value between max line width and min line width. That should be smooth. So to test this out, go to our good old sprite Reno, and then shove it in. Bam. What's not going on? What is not going on? Of course. There we go. Silly me, I've set the max and min line width to be the same for somehow. Now it's about 5, and its frequency is once per second. Actually, let's change the fragment function here a little bit to be a bit more efficient by instead of having to calculate get line width 16 times a second, we're going to have to we'll do it once. Yep. Slightly faster, I guess. As you can see, our lines here are a bit blocky, a bit irregular in the size of the deviations of the outlines. Well, I mean, it makes sense because we did break it up into regular blocks, but might want to add some bit of more variation to that. So in get line width, instead of calling noise once, what we're going to do is we're going to declare another variable, intensity. Wow. Which equals 1.0. Yeah, we're going to do a for loop. So for int I equals we're going to run it like 3 times ish. Sure. And then it's going to instead be w equals noise p s linear interpolated before as the previous value of w and intensity. Then every loop we're going to divide p by 2 and intensity as well. And for the original w is going to be 0.0. So this way it actually calculates 3 blocks of initial block size, and double that, and then double that. But every next block will have half as much influence over the first one in deciding how much deciding the width of the good old outline. It's a little bit less regular now. A little bit. You can also, of course, just decrease the block size. 5. Wow. And increase the frequency. Okay. So now we're going to do gradients for our outlines. That is, where it starts with one color at the edge of the image and then fades out into another one. Okay. Step 1 is to get the closest distance to a non-transparent pixel from the texture, of course within the radius of outline width. If you encounter something, change the pixel into a linear interpolation between a start color and end color. Otherwise, render the texture as normal. Alright, so now, let's implement the gradient one. I'm gonna go just duplicate outline material again. Wow. Cool. Okay. We're going to change our outline style to starting and ending color. Why not? Then we're going to want to create a function called. So we're going to want to create 2 functions. First one is a boolean is in range. So in range, and we're going to want to go. We're going to want a sampler 2D called text. So we're going to pass in a texture, and we're going to want to also pass in the UV that we're starting from, and we're also going to pass in the vec2, because it might not necessarily be square, of the distance that we're doing. It's going to be a little bit weird because we're not doing distance as a float, we're doing a distance as an x and y vector. So we're processing the x and y vectors values of the distance separately, but okay. So what we're going to want to do is just the same thing down here. We're going to remove, basically we just move the good old for loop in the fragment of the original outline to here, and then say if we find that a pixel that is not 0, you return, oops, we return true. Otherwise, we return, if we don't find any, we return false. Wow. Then, of course, so dist or scale, we can just straight to dist. Perfect. Plus texture is text. Instead of UV, we use UV. Solid view. Okay, and then we create another function called it returns a float. Get closest distance. Of course, similar to above, we import the texture, we import the starting UV, and the max distance. All of it scaled to the texture size, of course, or UV of the to a UV scale, of course. Then we're going to want to declare a constant right under res called, I don't know, grad res. Let's just keep it at let's also keep it at 16, why not? And then what we're going to do is we're going to do another for loop, so for int I, of the letter I, equals 0. I is, let's say, grad res, I plus plus. They want a vec2 dis, which is equal to float I divided by float grad res times max dis. And of course, max dis is of course a vec2. Again, piecewise. Yeah, x and y is one way, whatever. If pixel in range text uv dist turn float I divided by grad res, which should be a number between 0 and 1. Ooh, actually, to make it a number between 0 and 1, we're going to do plus. We're going to start I at 1 and do until it's less than or equal to grad res. We don't actually want the pixel to look at itself, obviously. And if nothing else, if you don't find anything, just return -1, which is a fail state. So now going back to our fragment, we can go scale equal, actually change that to scale dist, this text pixel size, times line width. And then after we do that, we declare a float w, not alpha because we're not actually looking at transparent. We're looking at more so the weight between gradients than the transparency of pixels now. So float w equals closest distance of texture, the UV of the pixel obviously, and scale distance, and texture thingy is distance 2. Then what we're going to do is we're going to make color a linear interpolation of starting color, ending color, as far as W for weight goes. Then let's test it out. Boom. Oh, it actually works. Okay. And then we can actually let's make line width a bit larger. Let's make it 10. Wow. Surprisingly, it actually works. Interesting. So, getting the closest distance, going pixel by pixel can actually be a bit slow, especially if we want to scale this up to like 100 instances of your line effect. So we're going to speed it up a little bit using binary search. To do that, we're just going to type in at the top, if not pixel in range, text uv max dist, return -1, so do the fail state of -1, and we can then create a, now we're going to create a variable high, float high equals 0.1, and low equals 0.0. And we emptied our for loop here. So in our for loop, we're going to create another variable with float cur as the average of high and low. And then we're going to check if there's a pixel in range x of current times the distance, the maximum distance. So we check out a distance of a fraction of max dist based on high, which is our upper bound for where the closest is going to be, and low, which is the lower bound, which of course starts at 0. If there is pixel in the range of cur, then that means that our upper bound of where the closest distance is now cur. So we change high to cur, high to cur. Otherwise, that means that the closest distance is not within cur. So we change low to cur. And then we just return high. Because the upper bound is as far as we can be sure that it definitely is at least as close as high distance away. But it might not necessarily be directly in between where the center of high and low is at that point, at that resolution. And what this does is, this makes it so that your texture will actually look at 2 to the grad res pixels. So you can actually reduce the grad res to 4, for example, and it will have the same effect as doing it, setting it to 16 with going pixel by pixel approach. Yep, so it's a bit faster. One more thing you can do is you can actually change the, you can actually run weight through a function before you linear interpolate. So if you, for example, wanted the starting color to last longer, you could square weight the n, going w times w. Hey, what do you know, the black line is a bit longer. If you wanted it to cycle between the starting and the ending point throughout the outline, something you can do is you can go w plus, of course, not equal to frac. See, it kind of pulses there a little bit. Maybe even minus time even to make it pulse the other direction. It's pretty cool. You could also let's change the starting color to white right now. You can also make the starting color last for a very short amount of time by running it through the tan_h function. And of course you can shorten the starting one even further by multiplying w within the tan_h function. Get this really cool thing. Yep. See, and this is how you can make a 1000-degree knife kind of like outline effect. And yeah. So I combined the changing outline and the gradient outline to get this. You know, that's what I call an effect. That is what I call an effect. This radiation thing too. It's cool. Yeah. One of the roadblocks you might face with outlines is cutout animation. So those who don't know, cutout animation is basically when you have a character that's made up of multiple images, and you move each image separately in order to simulate movement for the greater character. The problem that you might face is that in Godot and a lot of other game engines, shaders are handled separately for each individual sprite. So if you were to give each sprite of a cutout animation the same texture, then you're going to see their outlines go on top of the thing behind it, even though they're supposedly supposed to be one continuous body. Luckily, there is a way that we can get around this, though it is a bit convoluted. So as you can see, we have a scene with our animated character over here. Moving around. So what we're going to want to do is we're going to want to add a child to the scene that is a viewport. Then, we're going to want to make our little character a child of that viewport, and we're going to give the viewport a random size, big enough to hold the character. So I'm just going to make it the size of the screen. Then, the wacky part is we're going to add another sprite as a child of the main scene. And we're going to want to, for texture, we're going to want to right click it and go to the very bottom new viewport texture. I'm going to select the viewport that we just spawned in. As you can see, although it is a bit, this is why it's a bit scuffed, the way the viewports work with Engine. As you can see, our little icons there, because our character is inside the viewport, which itself is being projected to the sprite. In order to make this upright, we're going to go to the viewport, and we're going to turn V-flip off on render target. We're also going to just center it to the, more or less, to the screen. Then, the fun part comes in. We just go to the sprite that we're hosting the viewport as a texture, and we just add the material there. Okay, again, another reason why this is a bit scuffed is that you're going to have to select transparent background to make it so that the viewport itself will actually render up any area it doesn't use as transparent instead of this weird gray background color, which selectively counts as a color or whatever. Anyway, as you can see, the outlines don't overlap because it treats the entire composite image as if, the entire viewport even, as if it was one image. In fact, you can actually add more of it to the viewport. Wow. Add more sprites to the viewport. Add more characters to the viewport. Wow. Yep, and you can see they also don't overlap with each other. That's pretty cool. So yeah. Another problem you might face is that you can't actually directly drag items from within this viewport. You actually have to manually go in and type in their positions and stuff, which is a bit of a pain, but it does work. Yeah, so this is one way that you can not only have one cutout animation, one cutout character at work with outlines, but also have two separate characters just kind of overlap with each other and not have their outlines intersect, which might be what you're looking for depending on where you're going. Yeah, it's a bit scoofed. The other incredibly big disadvantage of this is that obviously you have to actually put every character and animation that you use inside this viewport, which means you either have to have the entire physics world in there, or you have to write a script that makes it so your sprite clone itself into the viewport and resync itself with its clone. There's no easy answer for stuff like this, and I'll leave it up to you to implement it yourself, to find an implementation that works best for you. Okay, so that was my video on outlines, I guess. Join me next time when I do something AI related again. Just wanted to get an easy visual one out.